back again here. You know what time it is. Make sure you pause the video. Try to find the answer yourself. You are cheating yourself. And I shouldn't even have to say this, but you are cheating yourself if you don't take the time to find your own answer and understand where you may or may not have went wrong. And don't worry, I'm going to try to explain it and try to make this video as short as possible. But, yeah, I'm doing this at work, so that's why I'm talking a little low. But make sure you pause, come up with your answer. All right, so the correct answer is, let me get the green marker. The correct answer is 100 hertz. All right. Just as a quick fun fact, you should know that human ears can only detect sound frequencies between 20 and 20,000 hertz. So if you knew that little fun fact, which I've seen it in a few MCAT textbooks, so I feel like that's something you maybe should know or just be cognizant of. But yeah, if you did remember that fact, then you would have been able to get rid of D automatically. Because it's unlikely. I mean, the question is talking about sound emitted by human vocal cords. So, you know, I highly doubt we will be able to produce speech that is that other humans would not be able to hear whatsoever. So if you knew that little fun fact, then you probably could have got rid of D. But enough of me blabbering on. Let's get into the actual physics behind this question. And the physics has to do with standing waves, particularly standing waves on a string that's fixed at both ends. All right. So I don't have time to dive into everything surrounding the foundation of this concept, but I'm just going to give you a really quick rushed version because I don't want to make this video terribly long. And pretty much I will preface by saying everything I learned is from some video on YouTube. I'm going to try to find it and link it in the description. I think it does an excellent job of explaining standing waves, where a lot of MCAT books that I've read and stuff, it's just been unclear. But I feel like this video made it very clear for me. So enough of me blabbering. Let's get on into why the right answer is the right answer. Okay, so something you need to understand when you get into under physics, once you get into the concept of harmonics and standing waves and stuff like that, is you need to be really comfortable with the concept of cycles. So cycles of waves. And understand that the cycle can be described essentially in 3 different ways. So we analyze a cycle by way of the frequency. We also analyze cycles by way of the period. And frequency is, that's the symbol for frequency. That's the symbol for period, which is a uppercase T. And we also analyze it by wavelength, which you should know is denoted by the lambda symbol, excuse me. All right. Back out a little bit. Okay, so cycles represent one unit of the repeating pattern of a wave. So a wave can be analyzed as multiple repeating cycles. So I'm going to draw a simple sinusoidal wave that you should be familiar with. So one that just goes like a roller coaster. All right, that's a simple sinusoidal wave. So frequency, period, cycle. A cycle, like I said, refers to it is basically the subunit of waves. So waves are just made up of a bunch of cycles, repeating cycles. And essentially, I'll jump ahead and let you know that this represents one cycle. That represents one cycle. And the reason it represents one cycle is that this position right here is identical to this position right here. Why? Because at this point, we're on the same point of the x-axis. We'll say that that's a position of 0. We're at the same point on the x-axis, and this wave is moving upwards. And if we follow the trail down, we'll see that we're at the same point on the x-axis, and the wave is moving upwards. So these two positions are identical. So the reason that this one is not identical is because it's moving downwards. Okay, so cycle represents a full repeating pattern that you could analyze by way of between two identical positions on the wave. Okay, so that begs the question, let's get into wavelength real quick. So wavelength is just the actual length of the cycle. And wavelength is usually measured. It could be either measured from one position to another position, or they call it a superposition. So we can call it superposition to superposition. Okay. But that's not the only way we can measure wavelength. The most classic two ways to measure wavelength is from trough to trough, or crest to crest. Okay. So wavelength is measured from superposition to identical superposition, or one crest to the next identical crest, or trough to the next trough. That is the way wavelength is measured. Now, the period represents the time that one cycle needs to complete, or the time that one cycle takes to go from one superposition, and the time it takes to go from boom to the next identical superposition. The time it takes for that path to complete is the period. So once again, the period represents the time it takes for one cycle to complete itself. And so period and wavelength look very similar because they analyze the same distance, but one is talking about the length and the other is talking about the time, but they're both looking pretty much at the same path along a wave. And the frequency refers to how many cycles complete. Let me back up. And frequency refers to how many cycles pass through a certain point within 1 second. So frequency is number of cycles per second. And so something you should understand and know is that, so if we're talking equations, you should know V equals frequency times wavelength. So wave speed equals frequency times wavelength. You should be familiar with that. For period and frequency, you should just know that period equals 1 over frequency. And then from there, you would just, if you need to find the frequency, depending on the question, you would use the period equation or you would use this equation. All right, so that's just a backdrop to waves and cycles. So when we're talking standing waves, like I said, I'm not going to get into the deep parts about it just because I don't have that kind of time. I don't want to make this video super long. It's already super long. But understand that you need to be familiar with two equations when it comes to harmonics, and that is the fundamental frequency equation and the fundamental wavelength equation. Forgive me that sound in the back. Again, I'm at work. So the fundamental frequency equation is derived from looking at multiple different standing waves. But the fundamental frequency equation, I think the best equation that I've seen is wave speed multiplied by the number of standing waves over 2 times the length. And the wavelength, the fundamental wavelength equation is 2 times the length of the string over the n, which represents the number of standing waves. Your fundamental frequency is your first harmonic. So your first standing wave. So standing wave number 1. So when you're looking for the fundamental frequency, n is going to equal 1 because we're looking for the frequency of the first, the fundamental, the foundational harmonic or standing wave. So n equals 1 is basically a long-winded way of what I'm saying. So for the question asks us the fundamental frequency. They give us the speed, which is 3 meters per second. And they tell us that we're looking for the fundamental frequency. So that's how I know that we're looking for the first harmonic, because fundamental frequency is equal to the first frequency or the first harmonic. These are synonyms. So 3 times 1 over 2 times, and they tell us that the length is, let me go back. They tell us that the length is 15 times 10 to the 3 micrometers. And then from here, you should be able to do the math without a calculator and arrive at the answer. But we'll do it together real quick. So 3 times 1, obviously that's 3. 2 times this number in scientific notation would be 30. So 15 times 2 is 30. Times 10 to the 3rd. Micrometers. And so that's a quick note that when you're oftentimes on the MCAT, you will need to convert to the base units, which is like just meters or grams. You want to get rid of the micro, the milli, the centi. You need to convert to the base unit. So real quick, let's convert micrometers to meters. So 30 times 10 to the 3 micrometers. We're going to put micrometers at the bottom, meters up top. 1 micrometer is equal to 10 to the negative 6 meters. So that is 30 times 10. We add the exponents. So 3 plus a negative 6. So that should give us negative 3. And that is meters. And so we have 3 over, and I'm gonna convert this real quick. So I'm gonna move the decimal place over. So that's 3.0 times 10 to the, and since I made this number smaller, I made this number smaller. So I need to make the exponent larger. So 10 to the negative 2. Let me put it right here. Oops. And we're just doing simple math right here. So 3 divided by 3 is 1. And this really, if it helps you visualize, this really looks like that. And so, at the end of my page. So 0 minus a negative 2 is plus 2. So 10 to the 2. And then 1 times 10 to the 2 is the same as saying 1, 1, 2. And the decimal place ends up right here. So that's how we get 100 hertz.